Hello, everybody, and welcome to another Ceph code walkthrough. I'm here with Patrick, and we're going to be going over specifically over the Ceph file system code base, in particular with the metadata servers, which is actually keeping various metadata on various objects inside of Ceph. So, Patrick, will you please take it away?
Okay. To start, I put in the chat an Etherpad with a broad breakdown of what we're going to cover. For those watching, please go ahead and open it up and you can follow along. So to start, I'd like to go through just a brief overview of what the different code bases that CephFS is on. Of course, most of the CephFS code lies in the Ceph source tree. There's three primary components of CephFS code, and that's in the source MDS directory. That's the one we're going to be looking at through most of this talk, which is all the source code for the MDS itself, which manages the metadata in CephFS. There's also the source client directory, which we're not going to be getting into, but that's where the libceffs and the fuse client lives, and all the code for handling talking to the MDS and also the OSDs. And then finally, there's another module here called the OSD or the Osd Object Cacher, which is used by both the MDS and the client. The client uses it to read and write file data to a range of objects, and the MDS also uses the object cacher to delete files, so delete the range of objects backing a file's data, and also to handle its journal. And then finally, there's another bit of code for those who want to get even more adventurous in the kernel, the Linux kernel itself, in the fsceph directory. That's where the CephFS kernel driver lies. Again, we're not getting into that today. So, starting with the getting into the MDS. A good place to start, as usual, would be the main function, and that is in this Ceph MDS directory. And unlike the rest of the MDS code, that's actually in the just in the top level source directory of the Ceph tree. And this is just a standard Ceph daemon that configures signal handling, reads arguments. So here's the main function. It configures its thread name, parses arguments, does some global initialization that's common to all Ceph daemons, and nothing too special about or unique to the MDS in this code, fairly common to all the Ceph daemons. The interesting bits here are when the MDS actually creates a messenger, sets some policies for the messenger, sets the bind address for the address and port that the clients are going to connect to, configures a monitor client so it can get access to the monitor map and the Mds map. And then here is the bit where it actually creates an Mds daemon, and that's a class that lies in the source Mds directory tree. And that's going to be actually the entry point for all the work that the MDS is going to do. And finally, this main function just does a wait in the messenger loop, and that's the place where it sits, letting the messenger pick up messages, and then the Mds daemon will actually handle them. When this method actually ends, that's when the Mds state is torn down. So this main function generally sits in this messenger wait loop. So getting into the MDS, we'll now talk about the Mds daemon. So this is the startup code for the MDS and also the handling for the standby state for the MDSs. All MDSs start in a standby state, waiting to be given a place in an MDS cluster for a file system by the monitors. So the Mds daemon will sit and listen for a new Mds map, and that's handled in this handle Mds map function. Open the C file on the bottom. And you'll see this method is actually called in a method called handle core message. And this is driven by this ms dispatch2 method. This is a method common for all messenger dispatchers in Ceph, where this ms dispatch method is called when any new message arrives. And the Mds daemon is going to try to actually process that message. So it's going to try to handle this as a core message. And it goes through a bunch of different message types. So is it a monitor map? Is it an Mds map? And so on. If it is an Mds map, it's processed here, coming back to this handle Mds map method. And this involves decoding the actual Mds map from the message. And then finally, processing it, and it's going to do a number of things for checking the state. So it's going to do a number of state transitions according to what the monitors tell it should be doing. There's a bunch of sanity checking in here. One of particular note is if it gets removed from the Mds map, then the Mds is actually just going to respawn itself. And so if you've ever run the Mds fail command, this is the code path it's going to hit, where the monitors remove it from the Mds map. The Mds gets the new Mds map from the monitors, seeing it's no longer there, and then it triggers this respawn method, which will just re-exec the executable. So again, there's a bunch of state transition code here for handling the Mds map. Notably, if it's actually not a standby Mds and it's an active Mds, it's going to hand this new Mds map off to the Mds rank, which we'll be talking about next, where further processing may occur. Let's move on to the Mds rank. The Mds rank is a fairly recent bit of code in Cephfs. It was added about 4 years ago as an abstraction for the state the Mds holds when it actually is a member of a Cephfs file system and not a standby. And this is where the Mds will handle moving between major states, like during recovery, when the Mds, during failover, when an Mds is starting up, it goes through a number of states, including replay, rejoin, resolve, etc. And this is all handled within the Mds rank class. So here it is. It's going to, let's see where. So this is where we're going to manage whether or not the Mds is in various states, is creating, is starting, standby, etc. The Mds rank is going to hold this or keep track of this state for the Mds daemon. It's going to handle some queuing for continuations in the Mds according to changes in state. We also have these methods for when the Mds hits certain bugs. For example, the Mds finds damaged metadata. It'll call these methods for actually notifying the monitors that the rank is damaged and then committing suicide, so it doesn't cause further damage to the metadata in the metadata pool. You see there's a number of methods for sending messages to clients. And Another bit of code here is that the MDS also keeps track of the MDS maps from other ranks. I'm going to use that to make sure that the MDS cluster is consistent in terms of what the state of all the MDSs are. And let's see. MDS rank is also responsible for handling its admin socket commands. So if you ever tell an MDS to drop its cache or list the sessions, this is handled in this method. Let's see. Now let's get to the core part of or where the interesting code is. So as we saw earlier in the Mds Daemon, it actually will dispatch certain, I don't believe we saw that. Let me open it up real quick. Right, so here's the ms dispatch to method in the Mds Daemon. If it doesn't handle this core message, for example, an Mds Map update or a monitor map update, then it checks if it actually has a rank, and if it does, it'll call the Mds ranks ms dispatch method. So coming back to the Mds rank, here we are. There's various checks here, but the making sure that the sources of the message are valid. Then we're calling into this dispatch method. And again, more checks are being done. For example, if the MDS determines that it's laggy, this is checked by the MDS sending a beacon or a heartbeat to the monitor clusters periodically, and if it doesn't receive an acknowledgement response back from the monitors, then it begins to believe that it's laggy or there's a network partition. In that situation, the Mds rank will actually just put the message on a queue waiting to be processed later until the Mds is no longer laggy. And this is one of those queues we talked about earlier, and this would be a continuation for that. Finally, if it's able to handle the message, it'll call this handle message method. And there's various types of messages that the Mds rank will receive. It'll receive messages from other MDSs according to updates to the cache. This is the migrator code path, so any subtrees that are being migrated between MDSs will go through this migrator dispatch. And then for setting up client sessions, this is all done through the server dispatch. In addition to the client request, which is the message that the Mds is going to be processing the most, perhaps with the exclusion of capability updates. Various peer requests from other MDSs, heartbeats from other MDSs. This drives the metadata balancing. We'll take a look at that later. Here's where the Mds locker will receive updates to the capabilities, or from other MDSs, lock messages that update the locks that the Mds has maintained for all the metadata. We'll look at that some more later. And also client capability updates from the clients themselves also go to the locker. So the Mds rank is sort of the gateway to all the dispatch loops for the other parts of the Mds. Right. Let's move on to the FS map. So again, the monitors keep track of all of the MDSs in the file system, and this is done through an FS map. It's similar to the Osd map. It's going to keep track of, and I should start out by saying the old way we kept track of the MDSs in the cluster was to what was called an Mds map, and this is still present in CephFS. But it was because we only had one file system, there was only one Mds map. And back when John Spray was working on adding multiple file system support to CephFS, we added this new class called the FS map, which maintains multiple Mds maps for each file system we might have. And that will, so here's the FS map that the monitor is keeping track of. You want to look at the data. This is hard to navigate on a small screen. So here's the main data structures that the FS map is keeping track of. The main one here that's interesting is this file systems list. So each file system has an identifier associated with it, and then this then a pointer to a file system class. A number of MDS roles, which is not actually persisted. This is just an in-memory cache of what MDSs are serving what file system. A list of standby daemons waiting to be assigned to a file system, and the epochs associated with those standbys. So looking next at the file system class, this is mostly a wrapper around Mds map, which, as I said, now we're having a number of Mds maps according to the number of file systems. So this class just holds three members. Used to be two as of just a week or two ago. This new one, this mirror info, is brand new. But this is just the cluster, the file system ID, and then also the Mds map for it. So I think that's the main highlights of the FS map. So let's move on to the Mds map. All the data members are at the bottom of the class. So the Mds map keeps track of a number of things, including this the epoch, which allows us to keep track of changes that have been made to the Mds map. This is mostly useful for the monitors keeping track of changes, but also clients that need to know if there's been an actual update to the map or not. Here we're going to keep track of the file system name, the max MDS. So when you're setting the max MDS on a file system to increase the number of file system ranks, that's where this change would be set. A number of data pools. So if you use the fs add data pool command, that data pool ID would be added to this vector. You can't actually set a file layout in CephFS without first adding the with a separate data pool without first adding it to this list of data pools in the Mds map. That's of course a form of protection because you don't want clients to be writing to arbitrary pools. We're also keeping track of number of Mds ranks that are available. So the in set is the number or the various Mds ranks that are in the file system. This will just be could actually just be an integer now rather than a set. It's going to be a consecutive Mds rank 0 to n, n being max Mds for the cluster. Here we also keep track of which ranks are failed or stopped or damaged. So again, if, as we saw earlier, an Mds might go damaged by calling that damage method, and that notifies the monitors that the rank is damaged. Then the monitors would note that in this damaged field for the Mds map so that it doesn't try to start a new Mds on that rank until it's been repaired. Also, we keep track of which ranks are failed and which are stopped. So if we decrease the max MDS and shrink the cluster, some of the ranks will be moved to stopped. Then finally, we also have this up map. So this is keeping track of which MDS IDs are actually associated with a given rank. We can take a look at, and that looks up into this Mds Info Map, which we can look at next. So this is another class or struct in the Mds Map, which supports, or is really just keeping track of a number of fields associated with an Mds Daemon, including its global identifier, the name of the daemon, so like MDS-A, which rank it's following, if any, what state it is in, and the file system that it wants to join. This is a new feature we added in CephFS to have, and to allow you to have an MDS join a particular file system. And also what addresses the MDS is on. So this is all kept track of in the Mds Map. And perhaps I should have mentioned, right. So, and here is the Mds State. So it starts out as state standby, but there's a number of states that that an MDS can be in, and that's here in this daemon state enum. And you've probably seen most of these if you've ever monitored a CephFS cluster before. Creating is done when we're creating a new MDS rank or restarting an MDS rank after shrinking a cluster and then growing it again. And then a number of states associated with failover. When an MDS starts up taking over for a rank, it goes to a number of these states. And I showed earlier that the MDSs keep track of what Mds Map other MDSs are aware of, and that's mostly to keep track of or to have consistent operation when they're doing recovery as a group. And that's important during especially cache, recovering the global cache, the state of the global cache. And then finally, state active, which is the default running state for the MDS. All right. Feel free to stop me with questions at any time. So the next thing we're going to look at is this Mds Server. Excuse me. Drink of water. And this is the module that's handling client request dispatch predominantly. So if we place to start here would be this dispatch method. Again, remember that the MDS rank calls this dispatch method if it's one of the types of messages that the server would handle. Here we have this switch based off of the message type, looking, and the server will fork off. Didn't say fork. It will call off methods for handling each different type of message. So here's the client reconnect. So during the MDS failover, one of the states is reconnect. If a client will try to reconnect during that state and then reestablish the capabilities and locks that it had with the MDS, that'll happen in this message handling. And then here we have a number of checks associated with looking up the session for the message. And then certain types of messages require waiting for active. So if the message requires that the server be active, for example, if we're just doing a standard make dir or open, then that message will be retried once the MDS becomes active. And then finally, another switch on the message type. Here we're looking at the client session. So whenever a client opens a new session with MDS, this is where all the bookkeeping for that would be done in this handle client session message. Then we have handle client request. This is where the main entry point for all the request handling in the MDS. Client reclaim is a new feature we added to CephFS recently to allow clients to reclaim old sessions that they may have lost. For example, with the primary use case of NFS Ganesha, to allow a new NFS Ganesha to reacquire the state that an older instance of Ganesha had. And then also peer requests from other servers. So let's look at handle client requests. So any client message that will access the metadata in CephFS will go through this code path. And there's a number of different types of client requests. And we'll see that in a moment. But this is going to do a number of checks associated with just any request handling. For example, waiting for the root inode to be opened, or getting the session and checking whether the session is valid. Moving on. Here we're doing some bookkeeping for the request. So if you've ever seen the MDS make note of slow operation for a client, for like a get adder that's being served too slowly, this is part of that bookkeeping. The MDS will track every request in this MD request class, which is in this mutation.h, which is going to keep track of, I'm going fast. It's going to keep track of all the metadata requests that the clients have, and this is going to keep track of locks, the distributed metadata locks that the client acquires as part of a request, and any other metadata, but also how long it takes to actually process the request. So that's created there, and then finally we're going to dispatch the client request. So here we're looking to see if the request was killed. If it was, then we're going to cancel it. This method may be called multiple times depending on the request needing to be restarted. For example, wasn't able to acquire all the locks that it needed when it first started. And then here we pull the message off the client request because we're going to take a look at it again. And here we're doing a number of checks. For example, this is a check to see if the file system is full. So we're looking at the type of metadata op we're doing, if it's doing a mutation. If the cluster is full, then it's going to respond with there's no space. Otherwise, we're going to get into more specific code paths, and that's going to be a switch based off of the type of operation we're doing. There's a number of, this is basically all the different RPCs that the MDS may process. For example, lookup, which looks up a particular inode. We have getAdder, which is looking up by path. SetAdder, which would be flushing metadata mutations on the client side to the MDS, for example, a change mod. There's not a separate change mod RPC in the MDS. It would all be processed through SetAdder. We have our xheader operations, directory reader, setting up POSIX files locks, creating a new file, link, rmdir, rename, makedir, symlink, etc. Again, notice there's no change mod. That's all done through setEditor. All right, so we don't have time, of course, to go through all these, so I thought we would just take a look at handle client getattr, which is akin to a stat in POSIX. So here again, we're getting the client request message, and we're going to be doing some basic checks on the message itself to make sure that it's a valid request. For example, the file name path can't be empty. If it is, then we return it's invalid. This is some newish code in MDS to batch up a number of getattrs into a single operation, and that's just to be more efficient with the locks in MDS, which we're going to be talking about in just a moment. Here we're going to get the inode associated with the getattr request. This goes to this read lock path pin method. And it's just going to be looking at traversing the file path. The main code path here is this MD cache path traverse, which is going to be actually going through the cache and looking up the inode by its file name. That's all we really need to say about that. Okay, so as part of a getattr request, we also issue what's called a capability in CephFS. So that's a type of lease. Although leases in CephFS there's also leases in CephFS, and they're slightly different. But there's an old file system concept from the 90s called a lease, which is a type of lock that clients get on metadata to ensure that that the metadata is not changed, so therefore they can cache the metadata and improve the latency of operations locally. So the MDS has fine-grained capabilities tracking the different rights that clients have on a given inode, including reading, writing, the file layout, the number of hard links on the file, what the state of the authorizations on the file, like the UID or the permission bits, etc. And that's all tracked through this MDS locker. We'll be looking at in just a moment. And it's all managed through this acquire locks. So up above here, we got this lock op vector. Apologies, I don't know what this fixed me is for, but here we're looking at the different things that the getattr is asking for. For example, we want the number of hard links for the file. We would be setting this cephcap link shared bit, and we would add a read lock for getting the link lock on the inode. This ref here is kind of poorly named variable. It's the actual inode associated with what we're doing a getattr on. And we'll see this later, but there's a number of metadata locks on the metadata itself, corresponding to who has permission to change it, or if we have a collection of read locks on that lock. We have multiple clients that want to have the link capabilities, so they know that the link count of the file and it won't be changed without being notified by the MDS. So that's one of these locks that it might acquire. Then the authorization lock, so UID, GID, mode bits, etc. The XAdder lock, so the client has the collection of extended attributes set on a file, so it would have this lock as well. And that's all controlled by what the client asks for, and the client can be can limit itself on what it wants, and that can help make sure the request is processed more quickly. If we don't have all the clients asking for write locks, which would require us to revoke a lot of permissions on other clients and slow everything down, so the clients can be minimalistic in what they ask for. And after adding all the different kinds of locks that the client needs in order to actually get this inode state, it's all driven to this MDS locker acquire lock. And the locker is going to be responsible for looking at each of the locks that are being asked for and trying to change the state of the distributed locks across all the MDSs and also the clients, and try to change and poke the state of the locks in a direction that gets us to a point where we can actually finish this request. You can see if we don't succeed, we're going to return, because it's going to be the operation will be retried later. But as part of trying to acquire locks, if there's conflicts, for example, another client has exclusive extended attribute permissions, and we're trying to get all the files inode state, then the locker actually needs to go out to send a cap revoke message to the client that has that extended attribute lock. And that's all driven by this locker module. Likewise, the locker is also going to handle issuing capabilities. So as part of acquiring the locks on this file, the locker is also going to take care of the details of issuing the capability on the inode in question, so that the client knows what it can cache according to the getAdder. And in a general stat operation, that would be pretty much everything, and it would have a read capabilities on all the associated metadata. As far as what a read capability would look like, for example, with the XAdder shared, that would be the XAdder shared, because it's going to be sharing the state with other clients. It wouldn't have permission to write, whereas Ceph cap XAdder exclusive would grant permission to make modifications to the extended attributes. And finally, we have this check to make sure that the client has permission to read that inode. And that would be, for example, we have in the CephX capabilities for clients, we can limit access based off of the network address or what path the client should be able to read. And that's all done through this check access method. And if the client lacks permission to read, then we return. And here we're going to set a number of fields in the reply that for this getAdder request, which we're also calling a stat in this debug message. And then we finally respond to the request. So there's various bookkeeping there. Here we're actually going to reply to the client request and make a mClient reply message. And there's various bookkeeping done on the metadata mutation. So that mutation class I talked about earlier, here we're marking an event that we're replying to the message. So if you did see a slow operation, you could see what events have been processed and when. And don't need to talk about all this. But here it's looking up the session and actually sending off the message to the client here. Okay. So let's go back to the Inode client get-attr. We spoke a bit at length about what acquire locks is doing, so now we can go have a look at that code. So here we're getting our mutation reference for the actual operation, the vector of locks that the mutation requires, and some other metadata concerning the auth pins. So here we're just, the locker is an incredibly complex bit of code because we're handling a distributed locks across MDSs and clients. But for those who are interested, and we're not going to go through this really at depth, but I wanted to point out, here's where the caps that we would eventually be issuing to the client. So there might be a set of inodes that we're going to issue caps for. And we call this cancel locking method, which is actually going to set the different inodes that we need to get locks on. And then finally, at the end of this really long acquire locks, we're going to actually issue the caps. So this actually differs a bit from some of the other code paths in the MDS on where the caps are actually distributed, and that's done in the locker itself. I think the reader path is handled slightly differently. So here's the issue cap set, and that just iterates to the set and we call it issue caps. And we're going to see this is where the locker actually issues the cap to the client. Here it is. We're sending the M client caps message to the client. All right. So again, the locker is a very complex bit of code. There's a state machine in the in this locks.c and h files. This is some fairly old code, which is responsible for managing the different state of the locks associated with each type of lock that an inode might have. I mentioned there were several types, extended attributes and authorization locks. And we would keep track of the different states that it might be in, and this corresponds to whether or not you have replicated metadata across the number of metadata servers and what capabilities each metadata server may have distributed to clients, and whether there are capabilities at all being issued to clients. That's all managed here. Let's see. All right, so let's move on to I don't think we'll get through all of this. The MD cache, another window, MD cache.h. So this is the structure that manages the global the cache for a given MDS rank, this is where all the management for changes to the cache are going to take place. Access to like traversing a file path is all going to go through the MD cache. So there's a number of structures that keep track of the metadata in the MD cache. So near the bottom, again, there's the various structs that we're keeping track of. Here's the Inode Map. So it's going to associate the inode number that we're all familiar with and the actual C inode, which is a struct for the cached inode. So you can look up the inodes that are in cache for the MDS through this structure. Similarly, for snapshots, we have a snapshot at inode. The root inode, all MDSs have that in cache and it's replicated. filer, which is again used for managing the or being able to delete file paths or file data, and then also setting backtraces on files in the default data pool, which allows us to keep track of the file path the file data is associated with if we need to do some kind of recovery. And then various state we need to keep track of the cache. And for example, uncommitted peer rename older is going to be used when we're doing rename requests that affect multiple MDSs. The state associated with doing the rejoin state for the MDS. And what else did I want to talk about? Subtrees. So also on the MD cache is a set of subtrees. If you're familiar with using multiple active metadata servers in Ceph, we have this concept of a subtree. So we'll actually split the file system tree into multiple pieces called subtrees, and they can be hierarchical and nested. And these are distributed across MDSs. Each MDS rank will keep track of a list of its own subtrees that it can see. If you have multiple layers of subtrees, some MDSs may not actually be aware of the full subtree map across all the MDS ranks. And it keeps track of the ones it can see, however, and then it also keeps track of the subtrees that are boundaries to that subtree. That's all done through this structure. So one of the, especially if you're looking at the server code and you want to, for example, add another RPC, one of the primary methods that of the metadata cache class is this path traverse method. And we saw that called earlier in the getAttr code path. And that's going to again take this metadata request method, a factory for setting up continuations if we have to retry the command later, so we can keep track of when it should finally be retried, what the file path of the path we're trying to traverse is, various flags, and that's done all in this method. So we're going to be looking at various flags in this, like whether or not we want the directory entry associated with the path, or if we need to get certain read locks as well. That can all be batched together as we traverse the path. So this is just going to get inodes and then recursively do path traversal as we peel off file names from the path. So this is all managed here, and there's a number of lock operations that we might need to do associated with traversing the path, and that's also bundled up into this method as well. For example, as part of path traversal, we might need to acquire certain read locks on a directory fragment as we traverse the path, and if we don't have it, then we need to retry. Similarly, we also have this frozen path. So I spoke about how the subtrees would be distributed across multiple MDSs. We might sometimes need to freeze the directory tree so we can ship it off to another MDS and delay mutations to that directory until it's been migrated to another MDS. So that would be part of this freezing concept. All right. I think that's all I want to say about this. But suffice to say, there's a lot going on in this path traverse method. So again, there's also this get inode method, and this just is a wrapper around the inode map, allowing us to find inodes. This is used in several places in the MDS for obvious reasons. And then also getting a directory fragment. So this is This dirfrag t is a structure for keeping track of the inode and the associated fragment of a directory. So talking briefly about fragments, in Cephfs, a directory may be sharded across multiple objects, and this is for efficiency and performance reasons. We don't want an object that represents a directory in Rados to have too many OMAP key value pairs. And so that may be fragmented into multiple objects. And those directory fragments can be distributed across multiple MDSs or just kept separate for space for performance reasons. But we can also, again, distribute them across MDSs so that we can improve throughput on a large directory by allowing operations on a given fragment to go to a separate MDSs. Okay. I think we're running out of time. Do we have a Q&A session for this, Mike? Hey, Mike, when AFK.
Sorry about that. My unmute button was blocked. Yes, we do usually.
Okay. Well, I kind of went through the code path for processing requests, kind of a whirlwind tour of the MDS, and I think where we just stopped was about as good a place as any. So do we have any questions so far? Otherwise, I'll just briefly touch on a few other parts of the MDS.
Also, everyone, you can use the chat in Blue Jeans as well. Don't want to say out your question. No questions so far. You're making everyone experts.
Thank you, Joe. All right. So if there's no questions, I'll just briefly touch on a few other files. So we have this in the MDA cache has is going to keep track of various metadata objects, and like for example, starting with the root directory, so you can do path traversal, but also the number of inodes that are in the cache. I talked about how there's the MDSs keep track of locks for each type of metadata object. One of the base class for all these metadata objects is done through this MDS cache object. And this is just an abstract class, find it, that keeps track of a number of different basic operations on cache objects, including inodes, directories, directory fragments, and also directory entries. And so there's a number of pins that we might have set on a cache object. For example, here's a pin for a request. So when we pin something to the MDS cache, we don't want it to be trimmed from the MDS cache if the MDS cache is too full, because there's a outstanding client request that is trying to utilize this object. And so this is a type of pin we might put on the cache object. There's also locked pins or replicated pins. So if metadata is replicated across a number of MDSs for performance reasons, we don't want it to be removed while it still has outstanding replicas. And then we have a number of states. For example, state auth, this is the most important one. This is just indicating whether the MDS holding this object is the authority for that object, and therefore has the capability to actually do modifications to the object, assuming that it has the required locks. And so there's a number of basic operations we have on here, like setting the state, checking whether we're authority. We have the authority state on the object. And then we also do some reference counting here as well. And some of this is just debug code, but we're keeping track of the number of references that are outstanding. So again, this is just an abstract class. So let's look at the C inode class. This is the cached inodes themselves. So C stands for cache, of course. So each inode in memory is going to inherit from this inode store base class. And this is all of the metadata that's actually persisted to the Rados metadata pool. And there's 3 primary structures associated with that. Let's dig it up. Here we are. Well, there's a number of things actually. There's the symbolic link string, if it is a symbolic link. The tree of directory fragments. So if this is a directory inode, we would keep track of what the directory fragmentation is on that directory. Another one is the inode data itself. So there's a same relatively new bit of code here, this inode constant pointer, which is just a shared pointer of this mempool inode, which itself is just this inode T structure. And we'll take a very quick look at that. So a lot of the metadata types in Cephfs are in this Mds Types Header file. And you can see that here. This is inode T. And this keeps track of a number of all the metadata that is part of an inode. Various methods on it. So here are some things that most people should find familiar. This is the inode, which is the inode number, the RDEV, the CTime, MTime, UID, nlink, etc. The file layout, which is a Cephfs specific feature allowing you to specify how the file data is sharded across a number of objects, the size of the inode, etc. Some basic metadata. Coming back, I think this will be the last thing we talk about, is just the cached inode. Coming back to inode store base, so this is just all of the data that's stored in the metadata pool. And for example, here's also the Xheader map associated with an inode. All right, and then that's inherited by inode store, and inode store is some C++ organizational class. Inode store bear, more of that. And finally, we have C inode. So you see that inherits from inode store base. And so the C inode is going to have a lot of the methods we need to keep track of pins and locks, what state the inode is in. For example, is the rstat information dirty, or is it frozen? Are we exporting the inode? And that's all managed here. One of the more interesting bits from a MDS hacking standpoint is this projected inode. So this is where we would actually make mutations to the inode. There's a vector of mutations on the inode, which we call projected inodes. So anytime we make a change to the Xheader map or the inode data, like the UID, we would store that in this projected inode struct. You can see the inode pointer and the Xheader map pointer here. And when those changes are finally persisted to the MDS journal, then we would pop that projection and actually set it in the main part of the inode class. As part of journaling, we have this projected inode concept. So I think I'm out of time. Again, there's other cache objects like this, the cache directory and the cache directory entry and cache directory fragment that have similar operations on them. And then finally, also the capabilities themselves, which are just a MDS memory concept for the locks that clients have to capabilities. Yeah, there's lots to talk about here. So, but I think we're out of time for this session. Any
That was a great
questions?
walkthrough, Patrick.
Yeah, thanks.
I'm looking in chat right now. I don't see any questions. Anybody still on the call have any questions? All right. Well, then I think that wraps it up for another Ceph code walkthrough. Seeing some thanks to Patrick in the chat. So thank you, Patrick, for taking the time, for giving us, even though it was broad, this was a very well in-depth walkthrough, I feel like. And appreciate everybody joining us live as well. And we do these every month. We'll have another one next month. And yeah, everybody for joining us.
Thanks all. Have a good day.
Thanks, everyone. Bye.